Space isn't silent. It's filled with invisible ripples carrying messages from the most powerful events in our universe. When massive objects collide, they send waves through the fabric of space itself, telling stories of cosmic violence and beauty. Gravity waves are like ripples in a cosmic pond, but instead of water, they're waves in space and time itself. When massive objects like black holes or neutron stars dance around each other and collide, they create these waves that travel at the speed of light across the universe. Think of space as a giant trampoline. When you put heavy objects on it, they create dips and movements in the fabric. These waves are incredibly important because they let us see things we can't spot with regular telescopes. They're our cosmic detectives, helping us understand how stars die, how black holes merge, and even giving us clues about the early moments of our universe. The really cool part? We can actually detect these tiny waves using super-sensitive laser instruments called LIGO, which can measure changes smaller than the width of an atom. Back in 1916, Einstein made a bold prediction as part of his theory of general relativity. He said space could stretch and squeeze, creating waves that would travel across the universe. But proving this wasn't easy. For nearly 100 years, scientists worked to build tools sensitive enough to detect these tiny ripples. It's like trying to spot a grain of sand from miles away. The challenge was massive. These waves are so small that by the time they reach Earth, they change distances by less than the size of an atom. Scientists had to develop incredibly precise laser measurements and find ways to block out everything from tiny earthquakes to passing trucks. The search seemed almost impossible, but researchers never gave up. They built bigger and better detectors, refined their techniques, and kept pushing forward. Their dedication would eventually lead to one of science's biggest breakthroughs. September 14, 2015, marked a revolutionary moment in science. After decades of searching, LIGO's detectors picked up a tiny chirp, the sound of two black holes crashing together 1.3 billion light-years away. These massive objects, each about 30 times heavier than our Sun, spun around each other in their final dance. In less than a second, they released more energy than all the stars in the visible universe combined. The signal was so clear that scientists initially thought it might be a test. But this was real. Humanity had finally detected gravity waves. This discovery opened a new way to study the universe, like suddenly being able to hear after only being able to see. It proved Einstein right and earned the LIGO team the Nobel Prize in Physics. More importantly, it showed us that we can now study cosmic events we could never see before. Let's look at how these cosmic giants create the waves we can detect. When two black holes get close to each other, they start a fascinating dance. They orbit each other faster and faster, like water swirling down a drain. As they spin, they pull and stretch the space around them. The closer they get, the faster they move. In their final moments, they're spinning hundreds of times per second. When they finally merge, they release a burst of energy so powerful it shakes the fabric of space. This energy spreads out across the universe as gravitational waves. The waves start out strong but get weaker as they travel, like ripples in a pond getting smaller as they move outward. By the time these waves reach Earth, they're incredibly tiny, but our detectors are sensitive enough to catch them. This cosmic dance happens regularly in space, creating a constant symphony of gravitational waves. While black holes make big splashes in space-time, they're not the only cosmic musicians out there. Neutron stars, which are incredibly dense stars about the size of a city, create their own unique patterns of gravity waves. When two neutron stars spiral together, they make different songs than black holes, higher-pitched signals that last longer and come with amazing light shows. These collisions are extra special because they create most of the gold and platinum in our universe. The waves they make tell us about the strange, super-packed matter inside these stars. Stuff so dense that a teaspoon would weigh as much as Mount Everest. Scientists can tell what's happening by listening to the changing pitch and strength of these cosmic songs. The technology we use to detect gravitational waves is a marvel of engineering. LIGO uses giant L-shaped tunnels, each 4 kilometers long, with powerful lasers bouncing between mirrors. These lasers measure tiny changes in distance when gravity waves pass through Earth. Imagine trying to measure the width of a human hair from a mile away. That's the kind of precision we're talking about. The detectors are so sensitive that they can pick up vibrations from passing trucks, distant earthquakes, and even ocean waves hitting the shore. To make sure we're really detecting gravity waves, we use multiple detectors around the world. When a wave passes through Earth, it hits each detector at slightly different times, helping us pinpoint where in space the wave came from. The future of gravitational wave detection is about to get even more exciting. Scientists are working on new observatories that will be much better at catching these space ripples. The Einstein telescope, planned for construction deep underground in Europe, will use a triangle shape instead of LIGO's L shape, making it 3 times more sensitive. In space, the LISA mission will create a giant triangle of satellites, each separated by 2.5 million kilometers. This space-based detector will help us hear lower frequency waves that Earth-based detectors can't catch, like the ones from supermassive black holes merging in distant galaxies. These new tools will let us see deeper into space and further back in time, maybe even catching echoes from the Big Bang itself. Gravity waves are like time machines, carrying messages from billions of years ago straight to our detectors. These waves tell us amazing stories about the universe's history, from the violent collisions of ancient stars to the leftover rumbles from the Big Bang. When we catch these waves, we're actually looking back in time, seeing events that happened when Earth was young or even before it existed. Scientists can figure out what kinds of cosmic events happened by studying the pattern of these waves. Some waves tell us about stars that died long ago, while others might reveal secrets about how galaxies formed. Each wave is like a puzzle piece helping us understand how our universe grew up. One of the most exciting developments in astronomy happened when we started combining gravity wave signals with traditional telescope observations. When neutron stars crash together, they don't just make gravity waves, they put on a spectacular light show too. In 2017, astronomers caught both the gravity waves and light from the same cosmic event. This double detection helped us understand where heavy elements like gold come from, showed us how fast gravity waves travel, and even gave us a new way to measure how quickly the universe is expanding. It's like having both your eyes and ears working together. You get a much better picture of what's happening. Now, every time we detect gravity waves, telescopes around the world quickly turn to look for any visible signs of the cosmic crash. The future of gravity wave research is set to revolutionize our understanding of the cosmos. Scientists are developing more sensitive detectors that could pick up waves from the early universe, potentially showing us what happened in the first seconds after the Big Bang. These improved tools might help us solve major mysteries like what dark matter is really made of and whether Einstein's theory of gravity needs updating. We're also getting better at quickly finding where these waves come from, allowing telescopes to capture amazing light shows from cosmic collisions. Some researchers think we might even detect waves from entirely new sources we haven't imagined yet. The next decade could bring discoveries that completely change how we see our universe. Thanks for joining me on this journey through the cosmic waves that shape our universe. If you enjoyed learning about gravity waves, hit that like button and subscribe for more space science. Share with friends who love exploring the cosmos.